we're going to get into the topic of signal aliasing. So last time we kind of were able to pull off a lot of different values from a graph from a signal that we've sampled, but the question is, if we're trying to measure an unknown signal, how do I figure out the appropriate fs, n, and t in order to capture my signal of interest? So let's figure it out, and let's look at some examples and some of the consequences of not choosing an appropriate n, fs, and basically t. Well, again, your n and fs will determine your t, as we saw in the expression below. But anyways, these are kind of the two critical parameters when you're trying to capture your signal. So let's look at some of this, what could happen if we don't choose our total number of data points and sampling frequency strategically. So let's look at an example below here. So what is wrong with this signal? So this is the blue is my original signal. So that's my signal of interest. That's the one I'm trying to capture with my sampling. But my red is what I actually capture. So red is my actual pulling out. That's what I'm reading from the DAC. What's the problem here? What am I, what's the issue with my sampling? Well, my f of s is way too large. Again, inverse time. So my sampling frequency is way too small. I'm not capturing my f of s. My sampling frequency is not high enough to properly sample my signal. Additionally, again, it doesn't even matter my n number of points. So what are the consequences of this? Well, and what frequencies am I missing? Well, I'm not able to hit these high frequencies in my signal because, again, I'm undersampled here. So my f of s is too small. It's not too large. Again, I'm always thinking of time. So your frequency is too small. So I'm not able to capture these high frequency undulations. I'm just getting low frequency signals here. And again, look at the danger. I might think, if I connect these points, I might think my function looks like this. And look at how I'm missing. I'm missing these high frequency, basically signals in my signal. So again, think about the implications of that. If you're designing a bridge, if you're looking at material properties, if you're looking at a cardiac signal, you could be missing these high frequency, that could cause arrhythmia. Or, I'm not a biologist, but who knows what could. I've seen a lot of medical TV shows. So in this problem, we've chosen fs that's not large enough to capture the properties of the signal. So when you undersample that original signal, now we think, okay, the signal we're measuring has a lower or a different frequency than the actual signal. So this is the first example of a concept that we're going to talk about a lot in this course, which is signal aliasing, which is where the sample signal, the red dots that we take and the ones that we connect, and we think, okay, we've sampled a signal and our signal looks like this. When we choose f of s incorrectly, so when we choose a sampling frequency that's undersampled, an f of s that's too low, our sample signal will take on a different frequency than our original signal of interest. So thus, we will assume that our frequency spectrum will be completely destroyed, and we're measuring a different frequency than the original signal of interest. So again, think about the implications of that. We are naively thinking, okay, this material is going to exhibit this type of, kind of properties in terms of frequencies, and it's completely different. So you could completely mismanage and select a material that's not appropriate for your application of interest. So we really need to know what are the real properties of our signals. We have to be really careful. Let's look at another example. What about this? I think the f of s here is pretty excellent, right? Like I'm hitting all kind of my points. So f of s, we're good to go. Okay, I'm happy. Anyways, it's good job on your f of s selection. But what's going on here? I mean, my n is way too low. I need more data points. I need to kind of continue along here. So here I'm hitting the high frequency. I can hit high frequency signals, but I'm missing these low frequency signals again that are going because I can't reach. I'm not capturing the full period of my material. So again, this is a critical issue. So it's the same problem here. I'm missing low frequency. I'm not capturing the entire signal. I'm missing low frequencies. So very similar aspect, and again, this could have drastic consequences to. It will affect basically what we're going to see here in a second, which is going to be your spectral leakage. But more on that a little bit later. So we need to make sure our sampling frequency is high enough, and we need to make sure our n, our total number of points, is high enough to capture the full properties of our signal. So missing out low frequencies, again, aliasing our signal. So we need to make sure we want a situation like this. Here, I've chosen my f sub s and my n large enough to fully capture. I'm hitting the high frequencies, I'm hitting the low frequencies. I am properly sampling my signal. So one question you may be asking is, all right, well, if I'm dealing with an unknown signal, how can I accurately or select my f sub s and n values? That is a really great question and a really hard one to solve. So if you're working with a completely unknown material, the best thing to do would do some literature review to see, or like some kind of test, or kind of what I always like to call some exploratory experiments, just to kind of try to see if you could determine some properties ahead of time. But the baseline you could do is always, if you have no idea where to start, you only have one DAC available, just run at the maximum values, largest S sub n, largest n values, and see if you could kind of work with that. And again, if you're concerned maybe there's some high frequency noise or low frequency noise, you can basically build in some low pass or high pass filters. But again, maybe some of these are frequencies that you really want to work with. But the point is, real experiments are very hard. So this is a real issue and a real problem. And whenever you're looking at these frequency spectrums or discrete Fourier transforms, we need to know what was the sampling frequency, what was the total number of points, what was the period, what signal are they trying to study? Did they choose the S sub s and n properly? Can you trust these frequency results? So it is really, really difficult in order to kind of do that. But in the next video, we're going to show, and we're going to actually get some quantitative value or kind of metric to avoid signal aliasing if we know, or at least if we know the frequency or the highest frequency of the signal that we're trying to measure. So we're going to do that next time, and we're going to look at the sine function. And let's go ahead and we'll tackle that in the next video. Thanks. Have a good one. I'll see you next time. Bye.